Good afternoon. My name is Brian,
And my name is Matt.
and we are second-year computer science students at the University of Exeter. This is our presentation for the module Outside the Box, Computer Science Research and Applications. The topic we will be focusing on is semantic indexing in full-text search.
Many of us on this course have been using Google Scholar to find out the most relevant papers out of the millions of articles already on the internet. A search for artificial intelligence returns 3 million results in just 1/20th of a second, and we rarely stop to think about how impressive this is. So, have you ever wondered how Google Scholar returns these relevant results to any query almost instantaneously? This is done using a technique called full-text search, and more specifically, semantic indexing. Full-text search is a way of finding documents in a database that match query keywords and ranking them algorithmically. A simple model for full-text search is the user enters a query to view results, the search engine filters results from documents it decides that match the query, then it ranks the results, and it sorts the results, for example by date, and finally it returns them to the user. The baseline method for full-text search is matching the search query with individual words in each document. This is neither efficient nor effective. Various techniques exist to improve the efficiency and effectiveness of full-text search. In this presentation, we'll be focusing on the semantic index developed by Bast and Bjorn Buchhold, published in their 2013 paper entitled An Index for Efficient Semantic Full-Text Search. In their paper, they propose a method for indexing articles semantically as a way of improving the efficiency and effectiveness of searching them. Through the use of ontologies, they were able to achieve query times of 150 milliseconds on a database of 40 gigabytes of text, which is very impressive. And this is a really exciting research topic because searching for things is such a big part of our everyday lives. It doesn't matter if we're searching for academic papers or doing online shopping. Having fast and accurate results can make a big impact on our lives because we do it so much.
The first full-text search engines were developed in the 1980s as a way of finding resources in large collections of documents. Many papers were published in librarian journals to show how libraries could take advantage of full-text search to help people find relevant books and articles. By the 1990s, full-text search facilities were common in online bibliographic databases. Throughout the 1990s, the size of the internet started growing rapidly, which increased the attention given to full-text search. There were some influential publications, such as Justin Zobel's An Efficient Indexing Technique for Full-Text Database Systems. This was a strong focus on improving the efficiency of searching gigabytes of text for keywords. In the late 90s, Google's search engine was launched and became one of the most well-known examples of full-text search and indexing. In the 2000s, there was much research into solving the synonym problem. It was found that online search engines such as Google could be improved by implementing systems which categorize synonyms and provide context to searches. Some work on the use of ontologies was published during this time. During the 2010s, ontologies became more predominant in improving the performance of full-text search, that is, using facts databases to query more efficiently. There was also work done on improving how full-text search algorithms dealt with word suffixes. Recent research has investigated using AI to improve search in library databases. This research represents a growing shift in the wider field of computer science, away from heuristics and towards artificial intelligence. Another trend is that more internet users are just using Google as a means of searching, rather than using built-in search facilities on specific websites. An example of this is using Google Scholar to find a paper published in the ACM, rather than using the ACM's search facility.
Exact word matching as a way of searching documents falls short in a number of ways. There are actually many challenges that arise when performing full-text search. A paper published by Jeffrey Beall called The Weakness of Full-Text Search does a really good job at identifying and outlining these problems, and we'll talk about them here. So firstly, homonyms, which are multiple meanings for the same word. For instance, the word football, which represents two different sports in the UK and the US. This can be a problem for full-text search if not addressed, because an American searching for football players would not want their results to be of a British Premier League football players, and vice versa with a British person. Next is negation. The problem with that negation represents is that a user can get the exact opposite results to what they're looking for. For example, a user searching for artificial intelligence recognition might be shown a document containing the sentence, "This image recognition algorithm doesn't use artificial intelligence, but uses a heuristic instead." This document would be returned because it contains all the query keywords. However, this is probably the opposite of what the user was searching for. Another problem is that it's just sometimes difficult for a machine to work out what the paper is actually about. Just because a paper includes certain words doesn't mean the paper is actually about those words. This can lead to irrelevant results being included just because the document happens to contain them, some of the words that the user searched for, even if it's not actually about them.
Some words with the same meaning may be spelled differently depending on the country the user is from. An example of this is the word analog, which is spelled differently in the US. This poses a problem for full-text search, because variant spelling of a word is not an exact match of the search term, so otherwise relevant results may not be found. Another problem is that words can have different forms depending on which tense they are used in. For example, a search for autonomous driving won't match a paper containing the sentence, "a car that drives autonomously." This is because driving and drives are not an exact match despite describing the same concept. This is known as the word stem problem and can be an issue for document retrieval because articles will often use a word in an expanded form. One more problem is synonyms, which are different words that have the same meaning, for instance, coding and programming. The concept is essentially the same, but a search for one may not give results containing the other in naive full-text search algorithm. This can lead to situations such as a student looking for guides about coding, missing out on useful results if they used the word programming instead. Last but not least, one of the main considerations in any method of searching is the speed at which results are returned. A portion of the challenge when developing a search algorithm is not just designing it to give accurate and relevant results, but for it to give them back in a reasonable time.
So, in the paper we're focusing on, Bast and Buchhold present a solution to some of these challenges. In this solution, a knowledge base of facts is used to narrow down the sample space of a search. This improves the speed of the searches as well as the quality of search results. So on the slide, this is an example of how their method would find documents for the query "astronauts who walked on the moon." It uses the knowledge base to determine that the phrase "walked on the moon" often occurs with people born in 1930. This narrows down the search space significantly, as it only needs to search for documents pertaining to people born in that year. So, this method is an example of semantic search. Semantic search is where the search engine tries to understand the meaning of a search query, rather than simply matching the characters in the query with characters in the documents. In the Neil Armstrong example, the search was processed semantically, because it did not only look for the characters containing the exact phrase, but rather determined some meaning or intent from the phrase, and then found documents matching that meaning. This method of searching leads to much more relevant search results than a baseline full-text search engine. A key part of the method proposed is the use of an ontology. Ontologies are knowledge bases of entities and facts about these entities. So, these can be used to help an algorithm understand the context surrounding the words in the search query. A particular ontology used by Bast and Buchhold is YAGO, which stands for Yet Another Great Ontology. At the time the paper was written, Jaeger comprised of 26.6 million facts, but it's now grown to the size of 120 million facts. Having a large ontology like Jaeger requires a suitable query method. The one used here is Sparkle. Sparkle is a query language which allows for the searching of fact triplets in a knowledge base. It was originally developed in 2008 and has become the standard for ontological search.
Before this paper was published, a known way of indexing using ontologies was to make an index for each document and also store any related words to entities in a document that are in the ontology. For example, when indexing a document about Neil Armstrong, the name Buzz Aldrin might also be indexed. The problem with this method is it can very easily lead to enormous index files, as some entities have a lot of relations. Another approach was to add words to an ontology according to which other words they occur with. For example, Neil Armstrong occurs with the word moon, so that could be added to the ontology. The problem with this is that if it's done for a large collection of documents, the size of the ontology explodes. The third approach, which was proposed and demonstrated in this paper, combines the two previous approaches into a novel method of indexing documents semantically without exploding index or ontology sizes. The index method proposed in this paper uses a joint index, which uses two different lists, one which stores the text occurrences of a word, and another to store the ontological facts about the word from Jaeger. Their solution allows queries to access both and combine the information from them to find relevant results. One of the goals of their system is to give the users suggestions while they are typing the search query. Such suggestions are given on platforms such as Google and Wikipedia. The goal informed their decision on how to structure the index of documents. Instead of indexing whole words such as astronaut, they instead indexed all the prefix substrings of the word, such as ast, astro. By doing this, their system is able to give results while the user is still typing the query, and the results get more and more accurate as the query becomes more complete. They used something called context lists to index each prefix of a word, with other words that often appear in the same context. For example, moon would be indexed under the prefix astro. This results in faster, more relevant search suggestions. This approach can help solve the problem of synonyms previously mentioned, as the word coding would be indexed with programming, meaning that a search for one could also include results containing the other. Usually, an index would take up a large amount of disk space, so compression is used to store the information in a smaller amount of space. A trade-off the authors of this paper chose was to use an algorithm which decompresses the lists very quickly whilst sacrificing a slightly larger file size in order to keep the search time as fast as possible.
The authors of this paper identified two concepts in semantic full-text search: entities and relations on these entities. They stored these relations in tables, such as a list of all the people they have as entities, and then the relation born on for the date each person was born on. They have separate tables for each relation, and this allows the search engine to speed up the search if it can determine a relation on the subject of a search. When indexing many documents, there are some commonly recurring relation trees. A least recently used cache was used to reuse these common trees and reduce duplication of computing. This helps speed up the indexing process. They also used a cache to store full-text search query results to increase the speed of future queries. The proposed method manages to deal with synonyms through the use of mappings, so individual words will be paired with an overarching word which encompasses all variations of that word. In an example the paper gives, the strings Neil Armstrong and Armstrong Neil will both be mapped to the same key, Neil Armstrong. Similarly, words like programming and coding could both be mapped to the same key, programming. So, This is how Bast and Buchhold's method manages to solve a number of the problems with full-text search.
In this presentation, we introduced the idea of full-text search and looked at its academic history from the 1980s up to the present day, where we described the current state of the art. We presented the challenges that face full-text search, such as homonyms, synonyms, and efficiency. We then showed how two researchers have partially solved these problems through the use of knowledge-based ontologies such as Jaeger, and context listing of words by their prefixes. This results in fast, accurate searches and search suggestions. The synonym mapping technique goes a long way in reducing the synonym problem by associating words with the same meaning with each other.
So, next time you search for something on Google Scholar, be sure to take time to think about how the search engine actually comes back with just the right results in such a short amount of time. And be sure to think about the work that goes into creating such intuitive algorithms that let search engines do this. And now for some acknowledgements. Firstly, we'd like to acknowledge that this presentation would not have been possible without the work of Hannah Bast and Bjorn Buchhold. Thank you to Wenji for his lectures on structuring and giving our presentation. And finally, thank you for watching. We really hope you enjoyed.